In this video, the unit commitment and dispatch optimization function is demonstrated using the Texas grid model. Study case 7.1 should be activated. The basic principles of unit commitment and dispatch optimization are explained in a video based on the standard transmission system example, but here we will look at some of the possible applications of the function. We will first show how the calculation can be applied to obtain a market dispatch profile optimized for cost. This will then be followed by a redispatch to take account of network constraints. And in the last run, N-1 contingencies will also be considered, and a battery storage model included. In this project, time characteristics are applied to the active power settings of all loads and generators. Looking at one of the generators, we can see the relative time characteristic that has been assigned. The generator has been selected to act as one of the controls in the unit commitment and dispatch optimization analysis, and has been configured with all the relevant data, including operating costs and redispatch costs. The unit commitment and dispatch optimization command is found in the optimal power flow and unit commitment toolbox. In this first study case, the aim is to optimize the generation commitment and dispatch over 1 day, using a DC load flow calculation. If we look at the objective function page, we see that these operational costs are to be minimized, but the additional redispatch costs are not included, because they are not relevant for this market-based optimization. On the Controls and Constraints page, the Controls panel shows which element parameters are available for the optimization. Only the active power settings of generators are to be changed. If we look at the power flow constraints options, we see that boundary flow constraints are to be taken into account. In this case, these represent market-driven limits, used to manage the cross-border flows. These boundary flow constraints are defined within boundary objects, and in this project are used to constrain the import and export of active power for some of the grids, for example the South Central grid. Branch flow constraints are not considered in this instance, so the calculation will represent a purely market-driven optimization. We execute the command. This button can be used to see the results. There is a summary page, and details for each calculation point, with results being available for each type of control element. These plots show the dispatch of the different fuel types before and after the optimization. We can see how the expensive coal generation has mostly been replaced by the cheaper gas and nuclear generation. And here, we see that the active power transfer across the South Central boundary is kept within the specified upper and lower limits. Now, if we open this command, there is an option to store all the new generator dispatch set points as time characteristics, with a new study case and network variation being created. This process of writing back results has already been carried out in this project, and the relevant study case is 7.2. So let us now activate that study case. Looking again at one of the generators, we can see the new characteristic applied to the active power set point. Our starting point, therefore, is a generation profile based purely on market costs. We can now carry out a further optimization where the network constraints such as maximum line loadings are also observed. On the Controls and Constraints page, the option Branch Flow Constraints Max Loading is selected. Changing the output of a generator away from its planned market position will incur a cost to the system operator, known as a redispatch cost. In this optimization, we should aim to meet the network constraints whilst also minimizing redispatch costs. On the objective function page, the option to minimize generator redispatch costs is therefore now also selected. The calculation is executed. On this plot, we see the outcome for the generator we looked at previously. The generator's output has been increased in the redispatch process. And in the lower plot, we can see how a variable renewable energy source generator has had its output curtailed. And here we see how these two lines, which were overloaded before the optimization, no longer exceed the 100% loading limit. As before, these results have been written back to the generators, and this new dispatch profile is found in the third study case. Now that the active power limits of branches have been met using a DC calculation, we will run the unit commitment and dispatch optimization once more, using an AC load flow, to ensure that voltage constraints are met. Contingencies will also be considered. The contingency dialog can be accessed using this link. In this study case, we have also included a battery storage generator. This generator is linked to a storage model, where the energy parameters are specified. The command is executed. Of course, the additional consideration of contingency cases increases the complexity of the optimization problem. For large networks in particular, the use of commercial solvers is recommended, as they greatly reduce the calculation time. But in this example, the default CPC solver is used. Now the calculation is complete. Let us look at how the contingency cases have been taken into account. In this plot, we can see that before the optimization the maximum post-fault flow was always much greater than 100%. But with the optimization, this is managed to around 100%. The minor excursions above that level result from the linearization that is used in the optimization process. In this plot, we can see how the battery storage element has been optimally dispatched, whilst observing the constraints of the storage model. In this video, we have illustrated some of the possible applications of unit commitment and dispatch optimization. In the first case, we did a market simulation, taking into account some limitations such as power exchanges between grids. In the second case we carried out a further optimization with network constraints being observed. And in the last case, an AC evaluation was used in order to ensure that reactive power constraints were met. We also took into account contingency cases, and showed how energy storage can be included as part of the optimization.